But what were we talking about? We're talking about the angle of parallelism, right? Last time we had, well, I didn't give it a name, but we had this angle, and let's just formally define it this time. So if points, seems dark in here. Now I'm imagining things. If points P, Q, R, and S, P, Q, R, and S are, as in this picture we had last time, so let me just draw it up again. P, actually, what are they called? Q, okay. Q and S, P and R. And the measure of angle QPR is this thing that we call D naught from last time. And measure of angle QPR is D naught, as defined last class. So remember last time we had this set. We had the set capital D. Capital D was a set of all possible angle measures that resulted in in PR intersecting this line QS, and D naught was the least upper bound of that set. So as defined last class, then angle QPR is the angle of parallelism. Parallelism. For QS and P. I'm taking a slight offense to something here. Where are we? Three, 6.2. Yeah. That's what I want to go with. Okay, so this angle is the angle of parallelism. As long as its measure is D naught, it's the least upper bound of the set of all possible angles that result in PR intersecting QS. And your first question should be, is this even well defined? What I mean by that is I'm only talking about these sort of half infinite rays that proceed in one direction, right? What about the other direction? What about over here? What if I do an angle going this way? Is the first ray that intersects also going to have an angle sort of less than that? Or the first ray that's parallel, is it going to have this angle of parallelism? So we have to answer this question, is this even well defined? But I just want to remind you once again that the way this works is this guy is the first, this is the first parallel ray. That's how you should be thinking of the angle of parallelism. It gives us this separating ray between parallel rays and intersecting rays. Right, so everything in here, all of these are intersecting rays. Those are guaranteed to intersect this line QS. Meanwhile, everything out here, everything past this first parallel ray, everything with an angle bigger than the angle of parallelism, these are all I want to say non-intersecting, but again, it's only non-intersecting in this sense of semi-infinite rays. The other side is going to cut through, but these guys, at least the rays just proceeding in that direction, they don't intersect. Right? They're all parallel. All right, so this is what the angle of parallelism is getting at, and I want to be very clear here. Look at the definition. This is the angle of parallelism for a line and a point, right? So in Euclidean geometry, it's the same for every single line and point. In Euclidean geometry, it's always 90 degrees, right? But we're working in neutral geometry and hyperbolic geometry, and in these cases, given a line and a point pair, each of them has their own angle of parallelism, and you have to look at them separately, okay? So yeah, there's this question of, is this well defined? I'm only looking at these semi-infinite rays. What if I want to look at the other direction? The answer is it's the same thing. This is well defined, but we have to answer this question. So, is this a well-defined definition? And the answer is yes, as the following theorem tells us. So let S prime, Q, and S all be collinear. If angle QPR is the angle of parallelism for P and QS, and angle QPR prime is the angle of parallelism for P and QS prime, then these two angles are congruent. Measure of angle QPR prime is equal to the measure of angle QPR. All right, so the hypotheses are describing a picture like this. I've got these 3 points that are collinear, S prime, Q, and S, and we're looking at the angle of parallelism QPR for Q and S, and then this point P, and that's this angle. And then we've got the angle of parallelism for QS, so still the same, QS prime, still the same line, and we've got this angle of parallelism QPR prime, and the theorem just says that both of these angles are congruent if those are the angles of parallelism for this line QS and the point P. Seems like a very obvious, very trivial result, but it actually needs a formal proof. And of course this would be bad, right? This would be bad if these weren't the same angle. Then you'd have to ask yourself, well, when I'm talking about the angle of parallelism, am I talking about this side of the line or this side of this line? Which angle am I talking about? So this is what I mean by well-defined, right? And now we don't have to ever talk about which side we're talking about because it's the same on either side. So it does need a formal proof. And we'll proceed indirectly, we'll proceed by contradiction. Suppose they're not the same. Okay, so let P, Q, R, R prime, S, S prime be as shown. So we'll just refer to that picture. Where angle QPR and angle QPR prime are the respective angles of parallelism. Okay, so we'll just assume our hypotheses, and I'm going to rely on the picture so I don't have to do too much describing of what's going on. So suppose they're not the same. If they're not the same, one of them has to be bigger, right? So we'll just assume QPR is the bigger angle, and assume without loss of generality that the measure of angle QPR is bigger than the measure of angle QPR prime. Okay, so we're going to show that this leads to a contradiction, but supposing they're bigger, or supposing they're not equal, one of them has to be bigger, so let's call this one the bigger angle. What does that mean? If this one's bigger, then I can choose a point interior to this angle so that those two angles are the same now, right? So, hence, there's a point X interior to angle QPR, so that angle QPX, measure of angle QPX is equal to the measure of angle QPR prime. Let me just get rid of these congruent angle pictures. There we go. What does that mean about this ray PX relative to QS?
It intersects it.
Yeah, PR is the first one that's parallel, right? So if this is a smaller angle, this has to cut through QS. So let's just extend it. Let's extend it to a point, we'll call this point Y, where it intersects QS. So because measure of angle QPX is less than the measure of angle QPR, which is the angle of parallelism, it follows that PX intersects QS at some point Y. It follows that this ray PX, if I extend it, right, not necessarily the line segment PX, but this ray PX intersects QS at a point that I'll call Y. All right, well, Y is a fixed distance away from Q. How about I come to this other side, right? We're trying to do some sort of symmetrical stuff here. How about I come to this other side and I choose a point Z that's the same distance away from Q. So now choose Z on this ray, or I'll say bi-infinite line, QS, so that Z, then Q, then Y, and so that QZ is equal to QY.
QS prime,
Uh,
does it matter?
Here or here?
Choose Z on QS.
Yeah, so I was thinking about that when I was writing it. Because I'm saying by infinite, it's still the same line, so it's somewhere over here on this.
Oh, I didn't,
it's-
okay, yeah, I didn't. see
Yeah,
that.
the arrow goes in both directions, but I suppose maybe in the sake of respecting the symmetry, maybe that's better. Yeah, QS prime and just extending in one direction. I'm a bigger fan of that actually. But both should be fine. Okay, well, what's happened in this picture? In this picture, I've of course constructed triangles. Everybody loves triangles. We're working with triangles because we know a lot about them. And I haven't indicated in this picture, but this is constructed so that that's a right angle. I chose this side to be the same length as this side. We have the same angles in both of these triangles, and of course, these two sides are congruent as well. So by SAS, these two triangles are congruent, right? Same two sides here, same two angles here, same two sides here. So by SAS, triangle, let's call it QPY, is congruent to triangle QPZ. What does that mean? What does that mean? Ah, where's the contradiction? Well, that means this angle is congruent to this angle, right? But we already chose this angle to be congruent to this whole angle. So these two rays, PR prime and PZ, are in fact the same ray, because this angle has to be congruent to this thing. So those are the same rays, but this ray intersects this line, which contradicts that this was the angle of parallelism to start with. So, yeah, we have to write this down, but there's the catch. So now, this means that measure of angle QPZ, measure of angle QPZ is equal to measure of angle QPY oops, that's an M. Measure of angle QPY. But of course, QPY is, of course, that's the same ray as PX, so that's the same as measure of angle QPX. And X was chosen so that this angle right here is the same as this angle right here. So that's the same as measure of angle QPR prime. Right, so this angle QPZ and QPR prime, those are the same angle. Therefore, these are the same rays, and PZ is not the angle of parallelism, or the ray that gives us the angle of parallelism. So there's our contradiction. So, what does it follows? It follows that PZ is the same ray as PR prime. contradicting that PR prime is parallel to QS prime. We never wrote this fact explicitly, that PR prime is explicit to QS prime, but this is by definition, right? Or not by definition, but by what we've proven. Because this is the angle of parallelism, this is a parallel line, right? So our contradiction arose by assuming that these two angles are not the same measure. Therefore, they have to be the same measure. So therefore, measure of angle QPR is equal to measure of angle QPR prime. All right, so we formally defined this. We talked about what the angle of parallelism was last time without giving it this name. Now we've just given it a name, and we've shown that our definition is well defined. It doesn't matter which side you talk about. So moving on, a couple of results about the angle of parallelism. First is that it's always less than or equal to 90 degrees. The angle of parallelism for a given line and a point is less than or equal to . Now, as far as I'm concerned, this is almost immediate. So this is just a very quick sketch. But if I have Q, P, and R, we've made this observation a few times, that what happens if the angle there is 90 degrees? If it's 90 degrees by the alternate interior angle theorem, alternate interior angles are congruent, therefore these are parallel lines. So if measure of angle QPR is 90 degrees, then PR is parallel by alternate interior angle theorem. And we've already proven that the angle of parallelism gives us the first parallel ray, right? So what does that mean? That means the first parallel ray, if this is a parallel ray, then the first parallel ray must be something less than or equal to 90 degrees, right? Has to be somewhere in here. The first parallel ray cannot be bigger than 90 degrees because here's a parallel ray already, right? So, because the angle of parallelism gives the first parallel ray, it follows, let's just say the result follows. To me, all of this seems 100% completely logically sound. So it's always been a little bit off-putting to me that the textbook does something much more detailed than this. Their proof is much longer than this, and it leads me to believe that maybe I'm missing something subtle here. Maybe I'm missing something about extending these rays in opposite directions, or sort of making them bi-infinite lines or something. But as far as I'm concerned, this works as a sketch, right? This is all there is to it. The 90-degree ray is parallel. The angle of parallelism gives you the first parallel ray, so it must be somewhere less than or equal to 90 degrees. So we're just going to go with this. I'm happy with this. Is that okay? All right, so if you look in the text, there's something much longer. Again, maybe I'm missing something subtle, but I don't think so. And as a quick corollary then, now we can stop talking about these one-sided infinite rays and make them bi-infinite. So as a quick corollary, if the angle QPR is the angle of parallelism for a line L and a point P, then PR is parallel to L. There's something very subtle here. Well, maybe not that subtle, but you might say, why am I stating this? Of course, we've already talked about this. Well, notice I'm no longer talking about just a single ray, right? We've already established this guy is parallel. Oops, QPR. We've already established that this one-sided ray PR is parallel. This statement is about the extended bi-infinite ray. That doesn't look very straight. Okay, so this is the bi-infinite line. So if you draw this one-sided ray with this angle of parallelism, well, now you can extend it in the opposite direction, and you still have a parallel line. Why is this? Again, we'll just write down a very quick sketch, but if this is the 90-degree ray, we know this side doesn't intersect because this is the angle of parallelism. And on the other side, since this is less than or equal to 90 degrees, on the other side, that angle must be bigger than or equal to 90 degrees, which is bigger than the angle of parallelism on this side, right? So again, a very quick sketch. Measure of angle QPR is less than or equal to 90 degrees. Which means the measure of angle QPR prime is bigger than or equal to 90 degrees. And of course, that is larger than the angle of parallelism, so, which implies that PR prime, that ray on that side, is parallel to L as well. nothing too profound is happening there. Just combining the two pieces together that we've done so far, the fact that the angle of parallelism is the same on both sides, less than or equal to 90 degrees on both sides. So if this guy's parallel, then over here, this angle is bigger than 90 degrees, which is bigger than your angle of parallelism. Okay. So now let's jump into what we're going to do with this. The differences between Euclidean and hyperbolic geometry here. And it turns out the reason we're studying the angle of parallelism is because we're going to use this to define hyperbolic geometry. There's many different hyperbolic parallel axioms we could take, or parallel postulates we could take, but we're going to go with something involving the angle of parallelism. So let's look at how these differ. Euclidean versus hyperbolic. And this first theorem is rather profound. It's if the angle of parallelism for a point P and a line QS is strictly less than 90 degrees, then there exist at least two lines parallel to QS. The book doesn't prove this. They leave this to, I believe, to an exercise maybe, or they just say the proof is left to the reader. Spend a couple of minutes thinking about this. Find two lines for me that are parallel to QS. Two different lines.
Is it two any lines or two lines through P?
Wait. Then there exists at least two lines parallel to QS through P. Thank you. You don't have to draw or write anything formal. Just draw a picture and try and find two lines that you know are parallel. Well, there's one, right? We always have this one. Just draw a perpendicular to the perpendicular. And what's another one? Well, yeah, the angle of parallelism is less than 90 degrees, right? So I could just draw a line where the angle is the angle of parallelism. So, D naught. So there's two. So what's an immediate corollary? Are there only two? Can I come up with a third?
The opposite.
So yeah, I could do over here. Can I come up with a fourth?
Anything in between.
Anything in between, right? So a fifth, a sixth, you can, how many can you fit in between these? How many numbers are there between something less than 90 and 90? Infinitely many, right? That's how real numbers work. So, yeah, D naught, and we've got 90. So there's our two rays we started with, but between the angle of parallelism, D naught, and 90 degrees, I can fit infinitely many more, right? So in fact, there are infinitely many. This is really profound. It sort of says that we can't be in this case. When you negate Playfair's postulate, when you negate Playfair's postulate that says there's a unique line, you might think the negation would be that there's more than one. Of course, we were already seeing there can't be zero because there's always at least one. You have this parallel or this 90-degree thing that always gives you at least one. But when you negate Playfair's, the formal negation is if there's not one, if there's not a unique one, then there's more than one, right? This says, in fact, the moment you have more than one, the moment you have two, you have infinitely many. And to me, it's really interesting because if we hadn't talked about any of this angular parallelism stuff, and I said, prove that if you have two, then you must have infinitely many, who the hell knows where to start with that, right? It seems like a very hard problem. I would have no idea where to proceed. But now that we've talked about the angular parallelism, it's very obvious. The moment you have two, there's two of them, well, by the properties of real numbers, I can fit infinitely many more different angles in between these things, so of course there's infinitely many. And I really like this, because for me this sort of gets into some of the philosophy behind math. Some people think math is just hard, and it's always going to be hard. Some things are hard to prove, some things are hard to work with. But I've always been of the opinion that if you set the right framework, and there's lots of history of this in mathematics, of things that were originally 100-page proofs are now proven in a single line. If you develop the right framework for thinking about things, then they shouldn't be hard, right? If something's really hard, maybe you just haven't thought about it the right way, haven't built up the right framework to talk about it. So now this theorem that seemed like it would be very hard to prove, with the right framework, with this angular parallelism stuff, is immediate, right? It's very easy to think about at this point. So I like that. That's where I fall on math. I think math should be easy. If it's really hard, maybe you haven't established the right way to think about things yet. So we're going to prove that Playfair's postulate is equivalent to the fact that the angle of parallelism is less than 90 degrees. This does one direction. We have the other direction to do. It's not particularly long, but we have 8 minutes or so. Puts us in a bit of an awkward spot, and I don't want to move too quickly through this stuff. So we'll stop early today. And yeah, I'll talk a little bit about the homework next time, but this homework that I assigned is not meant to be a hard homework. I believe the last two proofs are actually very simple, just piecing together the theorems that we've talked about. So there's And the first proof is just triangle congruent stuff, essay, and so on. But I'll talk a little bit about the homework next time if you want, and I'll see you then.